dy is equal to 120. Sorry, dy, not by. So dy 2.4. Yeah, it's dy. It's not by. I got it. No, it's by. By is correct. You did what am I doing? So by is equal to 120 times 10 to the power 3 Newton, and it's going upwards. Okay, I'll do it again. 160 power 3 times by 2.4 divided by 3.2, 120. Then we do summation about forces. In the y direction is equal to 0. So we have 120 times 10 to the power 3 minus by 160 times 10 to the power 3 plus by dy is equal to 0. So from here, dy is equal to 40 times 10 to the power 3 Newton, and is going up. Okay. So we find our reaction forces first. Okay. Next, we are going to construct a table. Okay, we're going to construct a table. Or we are going to divide the beams into different points or different sections. Okay. So we are going to divide into section. So let me put the diagram over here first. So we are going to divide into sections. Okay. So we are going to have section. Now the section can be a point or can be a range. Okay. So we are going to have point A first. Then we are going to do point A to point B. Then we're going to look at point B. Okay. Then point B to point C. Then point C. And then point C to point D and point D. Okay. So you create a table first. And then on the next one, you create the X. Okay. So the geometry datum is always on the what? Left-hand side. Right? Geometric datum is always on the extreme left of the structure. So this is 0. A to B means X will range from 0x to 0.8. Okay. At B, X is equal to 0.8. B to C is 0.8. X, it will go until 3.2 because 0.8 plus 2.4. And then at point C is 3.2, right? And then C to D is 3.2, X to 4.0, and at D is 4.0. Okay. So how many equations are we going to form, right? And how many of them are constant? So on your next table, right? So when X is a constant, it's going to, the shear force and bending moment are going constant. Okay. So this is a constant. This is a constant. This is a constant. And this is a constant. So when X is a fixed value, we are going to get what? Constants. Okay. Then from, if it's a range, it's going to be equations. Okay. And then from here, you're going to have you're going to have another table, and this will be on your shear force. It'll be your V, and then over here will be your bending moment. Be your M. Okay. On this diagram, the way it's loaded at point A, you have 0 shear force, you have 0 bending moment. Okay. So now we are going to start constructing our shear force and bending moment equation. Okay. Now, I'm going to assume down here, or those online, we have not a clue what is a shear force equation and what is a bending moment equation. I'm going to start you guys down from ground zero. I know some of you have done this before, okay? And some of you have not seen it before, okay? So we know at point A, we have 0 shear force and 0 bending moment because X is equal to 0, okay? So we are going to do from point A, point B. So the limits of the equation that we're going to form is 0, X to 0.8. That's the limit. So the equations that we form will be based on this limit. It's only valid for this limit. If it's more than 0.8, this equation cannot be used anymore. Okay? So we draw this. So point A, geometric datum, X, right? Over here will be 50 times 10 to the power 3x, right? Because the distributed load, let me get this diagram. This diagram is important. Because the distributed load is dependent on the distance what? X, right? The more the X value, the higher is the equivalent load. So it's 50X. And the distance from here to here is X over 2. Why X over 2? Because it is an evenly distributed load. We've done this before, okay? And then from here, we are going to assume positive shear, positive bending moment. Why? Because we are doing our analysis is from what? This is our analysis direction. So our analysis is from where? Left to what? Right. Okay. So now we do static analysis. So positive is going up. Summation about forces in the y direction is equal to 0. Okay. So we will have minus 50 times 10 to the power 3x minus by v as a function of x is equal to 0. Okay. So we have v as a function of x is equal to minus 50 times 10 to the power 3x. Equation number 1.
Eugene.
Yes, Opara.
Can you please explain the x after the force again? Like 50 times 10 to the 3x. Can you please explain why the x is there?
Because it is an evenly distributed load, right? And the distance is x, so it's 50 times 3 to the power 50 times 10 to the power 3x.
Right.
Does that make sense?
Yeah, makes sense. Thank you.
Okay. Right. So we have our equation number 1. So if you look at equation number 1, it is a linear equation. Okay. Right. Gradient is equal to minus 50 times 10 to the power 3. the y-intercept is equal to 0. Okay. And then the next one, we are going to do some mention about moment about the z-axis anywhere at point x is equal to 0. So where are we taking our moment? We are taking a moment at the dot that I'm drawing the circle now, when I'm highlighting now. This is where we take our moment. Okay. And then from here, we can determine our moment equation. Okay. So it's equal, so the 50 times 10 to the power 3x is going in an anti-clockwise. So 50 times 10 to the power 3x multiplied by x over 2, right? Plus by m as a function of x is equal to 0. So now m as a function of x is equal to minus 25 times 10 to the power 3 x squared. Equation number 2, second order polynomial.
So do we take this?
Okay. So in your mind, okay, what is the difficulty of this topic? Besides a lot of integration with a lot of stuff, you have to visualize the math, right? Now we are doing a lot of math, yes or no, to the equations, right? How does the equation look like? So this is my hint. It's a second order polynomial, okay? Equation number 2. So from here, we have determined our equation, okay? So we have determined like v as a function of x is equal to minus 50 times 10 to the power 3x. M as a function of x over here is equal to minus 25 times 10 to the power 3x squared. Okay. So those are equations. So the next point we're going to find now is at point B. As you can see, point B is going to be a what? A constant. It's going to be a fixed value, but not an equation. Okay, so we are going to look at point B. So at point B, where x is equal to 0.8, what is going to happen? Okay, so now we're going to sketch a free body diagram. Okay, so this is our point A and our point B. Now, again, the geometric datum is on the left-hand side, but we know that this distance now is equal to 0.8. Right, we know that distance is equal to 0.8. So over here, we have an equivalent load, which is 50 times 10 to the power 3 multiplied by 0.8. The distance from here to here now is 0.8 divided by 2. It becomes 0.4. This is your V at point B, and this is your moment at point B. Now at point B, we realize that we have calculated another load over here, another force, reaction force down there. And that is our By, and it's running at 120 times 10 to the power 3 Newton. We calculated that. Okay. So from here, we are going to do static analysis again. As I say, it's very repetitive. Okay. So positive is up, summation of forces in the y direction is equal to 0. We will have 50 minus 50 times 10 to the power 3 multiplied by 0.8. Right, it's coming down, plus by 120 times 10 to the power 3 minus by VB. B at point B. Okay. Now, why this is coming down and why this is anti-clockwise is because we make the assumption what? Positive what? Shear